Once you learn about electromagnetic induction, it's natural to start asking the question, all right, so if Faraday has showed that we have a current which is induced in a wire, and we'll concentrate on basically a coil or a loop, okay, within this video, then in which direction is the current actually going to flow when you do have a changing magnetic field? So Lenz, who was a Russian scientist, I think it was in the 1900s, sometimes in the 1800s. And so he has come up with, actually, by utilizing the law of conservation and thinking about, all right, so what is going to happen and in which direction is the current going to flow if you have a changing magnetic field. So his actual law is stated within here, and I've taken it out from the text that you see there on the screen. It states, if a changing magnetic field induces a current in a coil, the electric current is in such a direction that its own magnetic field opposes the change that produced it. So again, it opposes the change that has produced it. And that is where Lenz has kind of come across with the idea that this has to be related back into the law of conservation. So you can't really create, or destroy. You can only transfer energy from one to another. So let's take a look at some of the common questions, which come up, and try to see, all right, so which way is the current going to flow? Now, when we say current, we're meaning conventional current, right? So the electrons are actually flowing in the opposite direction. So if you would take, for instance, so a magnet that you see here on the screen, and you would take this magnet and you want to be able to find out, all right, so how is the magnetic field around this particular magnet? Well, we know that the magnetic field is going to be kind of flowing, out of the north. So let's assume that there is nothing else, within here. So it basically flows, in this direction. So that's the magnetic field. So in particular, let's just concentrate, at this instance, so this magnetic field, would be pointing out in that direction. So it's into what you see here. So it's a bunch of coils, and then you have an actual wire which is wrapped around in those coils, around some kind, let's imagine maybe some kind of an opening, just so that it allows you to have a nice coil all the way through. And we'll assume that this kind of continues on, and then maybe you have a galvanometer, or an ammeter, to be able to measure the current, or there's some kind of a circuit, around it. And now let's say we want to be able to move this into, and through the actual coil. So let's make it move inside. So now if you're moving it inside, then you do have a changing magnetic field, right? If it's stationary, nothing actually happens, because the current can only be induced if there's a change in the magnetic field. So if you're now moving this through the coils, then what Lenz has observed is that the way that the current in this particular wire should flow is in such a way that when it itself flows, it induces, so this is basically like a solenoid, so it will induce a magnetic field which will oppose the change. So it will oppose the change. It will always want to do kind of the opposition. So within here, if you're going to be moving this in this direction, so if it wants to oppose, so a magnetic field that would oppose the change, so this is going to be flowing in this direction, then we would have a magnetic field that would have to flow in the opposite direction in order to oppose it. But if you have a magnetic field, that would try to oppose this, so meaning it would try to flow out in this direction, then what does that tell us? So we can use a right-hand rule, within here, and we could see that the current would have to flow. So in this case, if we would wrap our kind of fingers around, so the current would have to flow in this direction, right? So it would basically flow in, and in that direction, because you would have your right hand rule, as you see there on the screen, and it's going to be pointing you in such a way that your north pole would be out in this way. Now, let's take this a little bit further. Well, what if instead you tried to move this inside? What if you wanted to move it away? Okay, so what if you wanted to be able to move this away within? So what is happening? So now you might think that, oh, it might still try to run in this direction. Well, that would actually be incorrect, because of the fact that if this is now moving in this direction, then again, what is happening to the magnetic field? So when it is very close to here, so if it's in this position, the magnetic field here is relatively strong. But as you start to pull it away, what happens is that the magnetic field starts to drop. So the north starts to drop. And therefore, so what it wants to do, it wants to oppose that change. It doesn't want to drop this. So in here, again, if you moved it in, it is increasing the north magnetic field. So therefore, okay, so this is going to try to oppose it. If it's now moving away, it is actually decreasing the north magnetic field. And therefore, this will try to oppose that, which means it will try to, increase that. So therefore, what would happen in here now, this would have been creating a south pole in here to try to reduce that change. And if it was the south pole that we would have, then therefore, the current would start to flow in this direction. Right? So if you take your right-hand rule, so you'll notice that you need your north on this side, so your thumb has to be pointing in this direction, okay? And then your fingers, okay, right there, okay, they would be wrapping around. So that's what would happen if you would start to pull it away. So Lenz's law is all about this. So now let's see a few more examples. So I'm going to go and do the opposite. So what if you started to flip this over? And let's say that it was the south pole. And now on the south pole, okay, let's imagine that now we're going to try to bring this inside. All right, so this is what we would want to be able to do within here. So if we wanted to be able to move this inside, so again, what would happen is it would try to oppose this. So you are increasing, okay, so within here, so the south pole is going to be increased, okay, within. So if I would do this, so remember that this is going to be kind of flowing out in this direction, okay, so into the south pole. So it wants to oppose that, okay, as well. So it's going to create a south pole as well. So one of the key things that you hopefully notice, so if you're moving a north pole into it, it's going to create, now it, meaning the current, the induced current, is going to create a north pole to counteract the other north pole when you're moving in. If you're moving in a south pole, it's going to counteract and create a south pole, okay, in order to counteract that. So within here, if you wanted to create a south pole over here, which means you would have a north pole over here, so what would that mean? Well, what that would mean is that the current would have to flow in this direction. So maybe let me draw that in here. So that current would have to start flowing in that direction in order for you to have that, okay, within. Now, if on the other side, okay, so if you go down in here and you start now moving this away, so if you want to move this away, you're decreasing the south pole. So that means you want to have the north pole. So on this particular side, so you're going to have a north pole within here, which would mean that the current would have to flow in this direction. So again, if a north pole is being brought into the coil, right? So you counteract with a north pole. If a north pole is moving away from the coil, then you counteract with a south pole, because you want to try to stop that change, right? Or at least nature wants to stop that change, okay, to have the law of conservation conserved within it. So that's what you would have, okay, within there. So that would mean if you're moving this away, this is going to have to be a north pole, and therefore, so as you're writing this in, so that north pole, you would have your current flowing in this direction, and notice current is flowing in the opposite direction, so to create your norths and your south poles. Now, you don't just have to move the magnets themselves, right? The magnet can be made stationary. So for instance, if I'm going to go back in here into these examples, so let's imagine that it is the magnet that stays stationary, but now what you decide to do is you decide to move the coil through the magnet. All right. So if you're going to be now moving the coil through the magnet, okay, so within here, so you have your North Pole, okay, and now you start moving your coil through the magnet itself. So is that any different than taking the magnet and then moving it into the actual coil? Well, it turns out no, it is not. Because if you start moving this in, so what you're doing is you are changing again, so the magnetic field, so from here, so from the north side, okay, as it goes in, if you are moving this into this, that's the same thing as moving your magnet into the coil. So what you're doing is you're increasing the north side, right? So it's going to counteract, okay, and try to repel that, okay? So it's going to create a north side here as well. And therefore, okay, so it will create a current which is going to flow in this direction. That's what you would have. And you can do exactly the same thing with, okay, the actual other side if you have south poles. So for instance, if you now take this, let me erase. So I'm going to just remove this out of the way. Okay, so now if instead, you know, what you had done is instead of moving the magnet away, okay, so let's imagine that now we're trying to take this, okay, within here, and we're going to try to run it through. So what you're doing in there is, you know, you are increasing, so the south, from the south pole, the magnetic field from the south pole is actually getting stronger, okay, as you're moving through, so therefore it will try to repel it, right? So try to create a south pole as well, okay, on that particular side. So if it tries to create a south pole, okay, within here, then from your right hand rule, okay, this is going to flow in that direction. And that's the same thing as if you were taking this and moving it inside of here. So notice if you took it, okay, notice that it has the same, okay, idea that you have this current flowing in this direction because it wants to create a south pole on that side, meaning a north pole on the other side. Now let's see this visually happen. So there's a really nice, okay, simulation. So this is, you know, from, you know, one of my favorites, so PHET. You can, I'll put up the actual link below as well, but you can take them in your search engine. So let me pop this up with a magnet and with these coils so that you can see also the current moving. Now please remember, current is conventional current that we're drawing. The actual electrons are moving in the opposite direction, all right? And we want to be able to see that. So I'll be right back. All right, so welcome back. So this is really cool to be able to see this because you can kind of simulate this out. So you can move your magnet, okay, around in here. And then you can also move your coils, and they have made the coils in such a way that you have a light bulb, okay, on top of it. Now you can change the light bulb, okay, to basically a voltage reader or, okay, a galvanometer that you have. I'll leave the light bulb, it looks a little bit cooler, okay, when it lights up. So, you know, let's see what our predictions would be. So again, so if you take this through, if we take the magnet and we move it into the coil, all right, so as you're moving in to the coil, so you are now increasing, all right, the north, so the magnetic field coming from the north side would have been increasing within there. So that means your coil is going to create a current in such a way that it also will create a north pole to repel it, right? So that's what it will do. So now we want to be able to see that, and what I would want you to look at is see they have electrons, so those little kind of blue balls that you have in there, they're going to be moving, and let's take a look at the direction. Now remember, they're going to be moving in the opposite direction of our conventional current, okay, correct? So here, okay, as you're going through, so notice it lights up, right? And then notice that the actual, so now moving it in and out, okay, so as you're going through in here, so as you're moving it in, notice that the electrons, okay, moved downwards. So what does that mean? If they moved downwards, the conventional current is upwards, right? Because it's in the opposite direction, which indeed shows us that your current, okay, is going up, and it creates a north pole on the left-hand side within here. Now, this is really neat because, you know, people might think, oh, you're moving it in and it's always going to be lit up. No, okay? It's only with the change that happens, right? So once you leave it there, there is no more change. So there is no current. So you have to kind of move this in and out, okay, as you're going through. And now, again, remember, as you're moving this out, right? So you're pulling away, so you're making the north side weaker. So it's going to make the current flow in the opposite direction, okay? So now they're going, so notice coming in, coming down, coming out, they're moving up. So in, out, okay? Because when you're moving out, so when they're moving upwards, right, the conventional current is downwards, and that means that the north pole is on the right and the south pole is on the left, which is exactly what we've described. So Lenz's law basically tells us that we can figure out in which direction the current will try to flow. Now, there's much more. This is purely qualitative because we're only interested in directions. As you keep studying this, okay, and you get further into Lenz's law, you can start calculating what the actual kind of, you know, currents, voltages, etc., okay, might be and what is happening within here. But when you're just starting off in your grade 11 physics or in a very foundational physics class, it's really cool to be able to see this happen overall. Now, the other component, just to end this video, okay, so I mentioned that you can move the magnets in and out, but you can also, you know, move this, okay, as well. So notice what I want you to see is within here, so take a peek, okay, in here. As I'm moving this closer, notice that the electrons moved down, and as you're moving it out, electrons move up. So the electrons moving down, okay, within here, so as they're moving down, the current is actually moving up, the conventional current. And what that would mean, it would create a north pole on the left, right? Which is exactly, okay, what happens. So you can either, you know, so notice that this, okay, electrons are coming down, right? Coming in, so they're coming down, or if you move the magnet, they're also coming down. So it doesn't matter if you move the coils or the magnet, you can create the current because your magnetic field is changing, right? So there's a change and then it induces a current flow. So I encourage you to take a look at, you know, this lab. You can notice that on the thing, they have actually multiple labs as you're going through, and I'll probably get to some of them as I create more videos. Okay, so they have bar magnets. This is the pickup coil. So this is the second one that you have. There's second tab on the left-hand side, okay, and you can play with it. All right, so that is it for this video. I hope that it gives you a sense and an introduction to Lenz's law. So it's a carryover from Faraday and his observation where you have an induced current. And now the question is, all right, if we have coils and we start changing the magnetic fields, you know, in which direction in the solenoid or in the coils does the current get induced? And we want to be able to understand that. And Lenz has captured that by basically stating that whatever direction you are choosing, okay, it has to create a magnetic field that will oppose the change that you have. All right. Thanks for watching. See you in a future video. Bye, everybody.